Hello, I'm Jamie, and I'm from Scotland, as you might be able to tell. This is the national dress of Scotland. It's a kilt, not a skirt, two different things. Thank you for joining us today. Hopefully you're getting the translation in your ears. Glaswegians speak at a very fast pace, so I'll try and slow it down. But we've got a lot to get through, as we're going to be sharing one of my favourite topics and what my PhD was on, and that is nanotechnology. So to get started, I wanted to introduce myself first of all and just say who I am and why I come to be here. And I decided to choose 3 images that I feel summed me up. At the right-hand side, there is me on stage as a science communicator, because I travel around the world talking about science. Because I love science and I love talking, so I love talking about science more than anything. In the middle is me at work. I wore a onesie to work, and that was because I work on nanotechnology. Things that are so incredibly small that skin or hair falling from me would be like a boulder coming down and crashing down on top of the things that I work on. So I wear that onesie not to protect me from the things that I'm working on, but to protect the things that I'm working on from me. The third image is me and Gates McFadden, Dr. Crusher from Star Trek. Why is Dr. Crusher from Star Trek on my slides? I'm a massive geek. It's part of who I am. I love sci-fi, I love fantasy. It flavors the way I view science and it encouraged me to do science. The other reason is because of the pose that we're in. As well as being a scientist and a science communicator, I'm also a dancer, so I teach people salsa. But that's not the plan today. But if it all goes horribly wrong, up on your feet and find a partner. Anyway. Today is not about me, today is about nanotechnology. And as a science communicator, I want to know what people think of when they think of nanotechnology. So to do that, I turn to Google. And I ask Google what it associates with nano. And if you Google the word nano, you get this. Now that's not nano. That's not even nearly nano. That is 3 billion times not nano. That's the nano car, which is 3 meters long and is on completely the wrong scale for what we're looking at. And it's not just cars that get it wrong. Another real annoyance of mine is the iPod Nano. So they brought this out. That's not nano. That's 7 centimeters long. So this is not nano. And what really annoys me is that the iPod Nano had a new generation that got even less nano than the first one. And that annoys me. Nanotechnology is something beautiful and something pure. It doesn't just mean something fancy and new. So let's have a look at the actual definition of nanotechnology. A bit of a wordy slide here, but I'm going to break it down a bit. The best definition of nanotechnology for me comes from the European Commission. And they have this very wordy definition here. And I want to break it down because it's got a few important elements in it. The first thing it says is about understanding and control. So when we're talking about nanotechnology, we're thinking about understanding something and controlling it. The second important thing, it's between 1 and 100 nanometers. So we're at incredibly small length scales. It's between 1 and 100. So over 100 nanometers, we're not really talking about nanotechnology. Third important thing, it says unique phenomena enable novel applications. Basically, different behavior means different uses. Nanotechnology behaves in an unusual way, and that means we can use it for new purposes. And the fourth important point, it lists a whole range of subjects that use nanotechnology. And so for me, nanotechnology is interesting because it involves a lot of subject areas. Chemistry, physics, biology, maths, engineering, they all overlap in the field of nanotechnology. And that's why it's so exciting. To get into a mindset of what nanotechnology looks like, it's always useful to start in the real world with something that we can see and understand. So a football is 2 or 3 decimeters across. If we take that decimeter and we shrink it down, dividing that by 10, we get down to centimeter level, where we have something like dice. Dice we can pick up, we can see, and we can manipulate. It's on a scale that we understand and we're familiar with. but we're still not at the nano level. We need to go smaller. When we get down to millimeter, we're starting to get down to the level where our eyes are struggling to see detail. If you think of something like a fruit fly, you'll see it whizzing around, but to see its eyes or its wings is difficult. We're getting to the limits of our everyday perception. We can go smaller again as we go down onto the down sub-millimeter level. So a fraction of a millimeter is a strand of hair. And if you've got long hair, you might be able to tease out a strand, and you can maybe just about see it and just about feel it. But when we get below millimeters, we're out of the range of human perception. And we need to take a big leap here. We go down by dividing by 10, dividing by 10, dividing by 10 again, until we get down to a micrometer level. And at a micrometer level, you would have something like a blood cell, which is about a micrometer thick. When we bleed, we can see the red color of our blood, but we can't see individual cells. So we're having to use technology to see and understand it. And we need to go down by a factor of 1,000 again, down to get to the nanoscale. And DNA that's packed inside our cells is 2.5 nanometers wide. And this is the level that scientists are working at the level of DNA, constructing devices that have unique applications. Really, it's down at the level of the atom. And just quickly, I wanted to take you through the history of nanotechnology, which is interesting how quickly it's risen to be an everyday term. In the 50s, Richard Feynman said there was plenty of room at the bottom, in a kind of groundbreaking lecture where he suggested we've spent a lot of time investigating big scientific phenomena, but actually maybe down at that atomic level, there's a whole world that we don't understand. So in the 50s, we didn't have a name for it. We weren't using it, but we're starting to think maybe there's something to be found. Fast forward to the 70s, and it got its name. Professor Taniguchi coined the term nanotechnology. So in the 50s, we thought about it. In the 70s, we gave it a name. We hadn't seen it and we weren't using it yet, but we were getting more sophisticated in our thinking. So the word nanotechnology was used for the first time in 1974. Leaping to the 80s, not only do we have a name for it, we're starting to be able to see it. IBM developed microscope techniques that allowed us to image things down at the nanoscale level. In the 80s, we got to see it, and we also started to get scared by it. This book, Engines of Creation, by Eric Drexler, came up with doomsday scenarios. The idea of miniature robots that were going to consume the Earth. And that was the stuff of sci-fi, and lots of Star Trek episodes are based on it, and Stargate. Science fiction loved the idea of the grey goo doomsday scenario. But it's really not realistic. So in the 80s, we saw it for the first time, and we started to be scared by it for the first time. And towards the end of the 80s, we were starting to use it and manipulate it. Here we have IBM's logo made up of single xenon atoms, painstakingly pushed into place to form one of the smallest pictures that's ever been formed. This is also where an odd trend in nanotechnology emerges. First, you learn how to do something, like push xenon atoms around. So what's the next thing you do? Not find a practical purpose for it. You do something fun. And so IBM went from making their logo through to making the world's smallest movie. And here, xenon atoms are positioned like a little kid kicking a ball to make the world's smallest film. And that's a repeating phenomena in nanotechnology. Develop a new technique. Do something cute. And so we need to think about how we're seeing small things. And microscopy is essential. It gives us a new way of viewing things. I'm a bit obsessed with microscopes, and I have them all around my house. Not ones that you can see at the nano level, but even an optical microscope can be quite interesting. And we can see how nanotechnology is changing the world around us. I started a little habit a few years ago of taking each of the phones that I got and putting it under my optical microscope that I've got here. The first one I started was with an iPhone 4, and under the microscope, the iPhone 4 looks quite different. To our eyes, we can see a nice, pretty clear picture, but under the microscope, we see the 3 different colored pixels. As iPhone got more sophisticated with its technology and moved from iPhone 4 to iPhone 5, at the same magnification level, there was quite a change. So we went from 4 to 5. And you can see the number of pixels doubles and the size of the pixels halves. A similar trend as they moved from the iPhone 5 to the iPhone 6. Pixels got a little bit smaller. We've got a few more in there. Something interesting happens as we go from 6 to 7, though. If I flick between the two, there isn't actually any change in size. By the time we got to the iPhone 6, we were making screens so sophisticated, our eyes wouldn't be able to see any smaller pixels anyway. So what's the point in making them even smaller? But that's one of the beauties of nanotechnology and the way it's changing the world around us in quite simple ways. In one way, it's just shrinking things down, fitting them more in, and making devices work a little bit better. But to get down to see the nano world, we need something stronger than a microscope here, because light itself just becomes too big. If you think of light as a wave, and you have a small particle, that wave can bounce off that particle and tell us roughly what shape it is. But if you have an incredibly small particle, the wave of light itself becomes too big to see the fine details on a nanoscale particle. And we need something smaller than a ray of light. So we turn to electrons. And with a beam of electrons, we're able to see things at a much smaller level. Things look a little bit different, but we can see with an extraordinary clarity. Here's a 5p piece under an optical microscope. It looks silver, and that's the 2 from the year 2019. If we put it under an electron microscope, it loses its silvery color. Electrons can't see color. They can see detail, but they can't see color. So we're bouncing a high-power beam of electrons off the surface of this. We're getting this gray picture back. This allows us to zoom in until it's unrecognizable, until the coin that we would recognize in our hand looks like something we've never seen before. And electron microscopes are incredibly powerful. This was an image that was taken at the University of Glasgow, where you can see columns of atoms. So we're down at the level where we're able to take photographs of what the atoms are doing and see the details. You might be able to see that there's lots of neat rows, but then there's also some distortion. And you can tell exactly what's going on in the structure by looking at it. And the world looks completely different down at that level. I come from Scotland, and this is a frequent sight. You might be able to see little black specks on the hat, which are midges. And if we look at them under an electron microscope, we can see their world in a whole different light. So here you can see all its eyes, you can see the biting mouth part. We can look at life down at the small scale and understand how it's working. Blue bottle larvae look like terrifying aliens. And also a little animal that is found in amongst moss, the famous water bear. We're looking at a water bear and working out, well, how does it sustain its life? How does it become able to cope with extremes of temperature? You can even send these into space and they would survive. So can we look at the nano level and learn from it and adapt to change our world by just looking at the nanoscale? And once we've learnt what things look like, it's time to work out how to control it. And it's difficult. If you think about Lego's like the atoms that we're working with. And you know how to build a little Lego house. You take one piece and you stick it on top of each other, and you build a little Lego house or tower. But unfortunately, atoms are much smaller than Lego bricks. So we can't just pick it up and put it together. As scientists, what we need to do is create the conditions where the house can build itself, so that the atoms will want to stick to each other, and we can form complex structures without pushing each atom into place, but creating the correct conditions for something to grow. And you can see nanostructures growing almost like grass on a surface, because we've created the correct conditions for them. So why should we use nanotechnology? And there's a huge many reasons why we might use it. One of the simplest to understand can be explained with an apple. Apples will stay fresh for a long time. But if you take a bite out of it, you'll see that the apple will quickly start to degrade. As oxygen from the atmosphere attacks the flesh of the apple will start to turn brown and corrode and rot away. And so if you have an apple that's cut in half, it'll degrade quite quickly. If you had an apple that was chopped up into lots of pieces, it would degrade all the faster. And what this is telling us is about surface area. The higher a surface area that air can be exposed to, the quicker a reaction can be. With nanotechnology being so incredibly small, it actually has a huge surface area. It's like taking the apple and smashing it down into the tiniest of particles, creating a huge, unimaginable surface area, and so how quickly it can react with the air. And that's something that we're using. For example, with hydrogen. Hydrogen and transport is nothing new. The Hindenburg disaster was using gaseous hydrogen, and it had disastrous consequences. We also use liquid hydrogen for fuel as well. So when you see rockets going into space, those are clouds not of smoke, but of steam, as hydrogen and oxygen are burnt together to give off plumes of water vapor. But this is difficult because liquid hydrogen is quite a difficult thing to store. And also, if we want to use it for cars and everyday vehicles, we need to think of something really safe, because my gran drives, and the idea of my gran driving that terrifies me. So we need to think of ways of making it really controlled and safe. And we can use that high surface area to create powders that store hydrogen on the surface. So the dangerous hydrogen is still there, but it's locked away on the surface of a crystal. And when we want it, we can get it off. When we don't, it's locked away. So we store it in a very compact and safe way. And this is one of the really active areas of research just now. Hydrogen storage, working out how we take that gaseous hydrogen, use high surface area materials, and store hydrogen instead in a canister. So you could go to the garage and you could just change over canisters to get more fuel for your car. It also, nanotechnology gives us a huge range of uses as well in terms of surfaces. Nanotechnology can be used to make something slippy. So if you look closely at a lotus leaf, if you look at its microstructure, it has a very irregular surface. It has little towers and pits, and that irregular surface means that water can't stick to the surface of a lotus leaf, and water just rolls off. Scientists look at this structure from nature and see if they can replicate it in the lab, which they can. If you create the surface of a lotus leaf instead on a surface, like on the screen here, water won't be able to spread out on that irregular surface, and it will stay instead as a droplet, and it can bounce or roll off. If you take this technology and you were able to coat an entire ship with it, you could reduce the energy used to power a boat by 25%, because the boat would repel the water as it was gliding through the water. It can not only make surfaces smooth, we can also make them sticky. And again, we learn from nature. Geckos can walk up walls, even walk up incredibly smooth surfaces like glass. And it's because of the structure on their feet. Again, if you look on a gecko's foot under the microscope, you'll see all these little pillars. It's got a very high surface area. And that structure allows the gecko to stick to walls. It doesn't have glue on its feet. It's a structural property. The shape of its foot allows it to stick. And again, that's something that scientists can learn from and copy, and it's been done. So this is gecko tape. Gecko tape has pillars on the surface that replicate the gecko's foot, and it was used to prove that a Spider-Man could be stuck from a pane of glass upside down. And again, this isn't glue. It's not a sellotape that's sticking Spider-Man to the glass. It's a structural property. So in theory, that could be unstuck and restuck many, many times because you're not relying on glue. It can also be used in medication as well. So these are stem cells. Stem cells have the ability to divide into other types of cell. And sometimes you want them to, and sometimes you don't. On this pattern here, this was work done in Glasgow, there is actually two different nano patterns happening. On the right-hand side is a regular grid. You can see all those little nano holes are quite regular. On the left-hand side, they're semi-regular, and they're spaced out just a little bit less regularly on the right-hand side. What scientists found was that if you put a stem cell on a regular array, it will stay quite happy. It won't differentiate. It doesn't turn into a different type of cell. But if you put the same stem cells on a surface with a slightly irregular array, the stem cell will stretch out and want to become a bone cell. And so just by controlling the shape of the surface that the stem cell sits on, we can control how the stem cell behaves. And so nanotechnology is evolving all the time. We start off with some simple use for it, and gradually we get to a more complex use. I want to stick with the body and mention the idea of the robots going inside our body. This is something that people have thought about and dreamt about for a long time. It's something that one of the doomsday scenarios almost kind of predicts. It's this idea of the miniature robots going into our body and damaging us or healing us. But let's think this through. If we decided that everyone in this room was now a cell inside the body, so we're all blood cells, say. If some cells were to be damaged, then we've got a damaged area. So let's say up in the back corner, we've damaged some cells. Now let's think about how we're going to fix those cells. There's a few different options that we have available to us. Just trying to sort my options out here. The first thing we could do is close the doors and kill all the cells. Healthy, unhealthy, let's just kill everyone. It solves the problem. Gets rid of the bad cells. But it has the downside of killing all the cells. Another option might be that I throw myself off stage, I fight my way back and kill just the damaged cells. Seems a more sensible option. In that way, most of us survive. The damaged cells are destroyed, but also I'm quite large and I would leave a path of destruction all the way up there. So it's not the ideal solution. I've got another potential solution on stage with me here. I'm going to have a little try at getting going. Seconds. See if it's going to work. No, I'm not seeing it. Not seeing it. So I've got something here that would maybe work. So this is a drone, and we could fly the drone, fly just to that damaged area, crash it into you, and kill just those damaged cells. That seems the ideal solution. Everyone else is left unscathed, but the damaged cells have been destroyed. So something like a small flying device seems a perfect solution. But there's a few problems with that. If we want to build something like this drone on the small scale, we need to think about how we build the propellers. We need to think about how we build the camera, the battery pack, the antenna. There's a huge amount of pieces go together to make this work. If you think back to the Lego example, if you start to build something, the more complex it gets, the bigger it has to get. And so if we want to build something on the nanoscale, we can't build something as complex as a drone. The idea of the fantastic voyage of going inside the human body with a spaceship just isn't realistic. But that doesn't mean that we can't do amazing things. Just because nanotechnology is never going to look like a miniature submarine. It's not going to look like a robot with a terrifying grappling hand that will invade your body. Doesn't make it any less amazing. Instead, nanotechnology is going to look just something like this. It's going to look like a cage of atoms where we could maybe put medicine inside that we could launch into the body to find just the damaged areas, to deliver the medication where it's needed. It doesn't look as fancy as a drone or a submarine or a spaceship, but it can do the job just as well. And so where nanotechnology is going to go in the future, I can't exactly say. But what I can say is it's not going to be a doomsday scenario of miniature terrifying robots. It's going to look like something quite plain, but it's going to do quite amazing things. Thank you very much.